Okay, so there was a question in the chat, a private question sent here. Is there a certain way we need to submit homework B5? It's easier, this person said it's easier to write out versus type. Don't have access to a scanner. Would submitting photos of the work via Canvas be okay? So the way we do this for homework B5 is if you prefer to write it out, as long as it's legible, that's okay. But what I prefer, and a couple of people have already uploaded images, and the downside of just uploading the raw images, so let's say you take a picture of it with your camera, even if it's legible, what Canvas takes those high resolution photos from your cameras and it makes them gigantic in the grader, so that when the TA is grading, she has to pan around this huge image in order to try to, it's like reading with a magnifying glass or something like that. And so what I ask people to do is, after you get your images, then put them into a Word document. You can like embed them into, so I'm not asking you to type them up in Word, but I'm just saying, like, take the image and embed it, like, you know, on page 1, like put page 1 image, and on page 2, put page 2 the image, and then upload that Word document or a PDF of that Word document. And that will sort of force the proportions to ones where when they're rendered inside the grader, they'll be readable. And so Corin mentioned that there's an app called Genius Scan that can email you a PDF of whatever you scan from your phone. So yeah, if there's other options, that's great. It's easiest for us. The Word documents just tend to function really well with the speed grader. And then it helps guarantee that, like, the proportions stay within the image. So that's kind of my preferred way, but yeah, there's probably more than one way to skin a cat. And I'm seeing, are there any other questions here? And I think that's, yeah, so there's some great, please check out the chat. It looks like there's some great recommendations for scanning. So, and thanks for offering those recommendations. I really appreciate that. I view the chat, by the way, as like a real asset, and a lot of people turn off the chat because a lot of faculty get like really distracted by it, and it is, I guess, a little distracting, but no more distracting than somebody raising their hand. And I generally find that students are really responsible in the chat. I mean, knock on wood. And I really think it's great when you guys can help each other like this, or remind me to turn on my camera or whatever. So so thank you for making excellent use of the chat. The other thing was, last time someone asked a question about condors and that cost curve, and I totally missed it in the meeting pulse questions, and I apologize for that, but I will give you an answer to that question today, because we'll do it. I'll flash that up here in a second. All right, and let me get rid of this sticky note thing. All right, any other questions? I do have a minor announcement. Two actually quick announcements. So one, I have to be on an NSF panel on Thursday that happens to stretch across the time for this class. And so for Thursday, I'm going to have to pre-record this class. And so everyone will be asynchronous. And so the attendance questions will still work the same way. So I'll still stop at times, show an attendance question, and have people fill it in and things like that. So it's not going to be like the lecture size where I put in quiz questions or anything. It's going to be pretty simple. It'll just be, 75 minutes, but you can pause it at different times or whatever. So basically, it's as if everyone skipped out on synchronous class and decided to just watch the re-recorded lecture. That'll be on Thursday. I should be out of the panel before my office hours. And so if you'd like to come to my office hours, talk about homework B5 or whatever, I should still be able to do that, because fortunately the East Coast, it'll be end of business for them. But during the class, I unfortunately have to pre-record. And so that is, I will send out a Canvas announcement about this as well, just a heads up. The other heads up is that you may have seen that late last week, there was an announcement that ASU is going to go all online after Thanksgiving. So normally you go, there's the Thanksgiving holiday, there's a week of classes, and then finals week. And so ASU didn't want people going, visiting their families and then just coming back for a week just to leave soon after that. And so instead they said, we'll just make it all online, and then that way people could kind of leave sooner. And so that that it really doesn't affect us very much because we've kind of been online anyway, except there won't be the in-person component for that week that people can choose to go to. But the real hang up is that they also said that all final exams have to be given in the last week of classes by the last day of the regularly scheduled class for that class. And it's a little confusing because they haven't changed the grade posting dates. The grade posting dates are still after the original finals week. So they've canceled finals week and are now telling us that even though our exams will be online, they have to be during the last week of classes. Now we're seeking some clarification to try to understand this because it seems like if our exams could be online, then it should still be possible to spread them out over finals week rather than just cramming all of the exams and the last week activities into one single week. It seems like that would be really hectic. Now, for us, we actually already planned for the final exam to be the last day of class, and then we had a makeup exam that was going to be showing up in finals week. So either I need to figure out to kill a lecture and move things around to try to put 2 exams during the last week of classes with only a day separating them, which I'm not really, I'd rather not do that because it's a lot of, it requires a lot of rejiggering of the curriculum and it ends up not being, I think, that much of a benefit. If we're given the flexibility to still give online exams during finals week, we can just continue as normal. So I just want to give you a heads up. If you notice that announcement, I'm working on it to figure out exactly what our options are, but you should know that, you know, in some of your classes, you would imagine there's going to be some sort of adjustment because we're not technically, I guess, allowed to give final exams during finals week. We have to give them during the last week of classes. At least that's currently how it appears to stand. All right, and I think that is, so any other questions or general questions or about course policy or assignment due dates? I did extend the due date for homework B5, so it's due on Sunday to give people a little extra time because I haven't seen a lot of people emailing me questions about it or coming to office hours, and I just want to make sure I had one more office hour in there, so it's due on Sunday night. So you've got a little more weekend time to work on it. All right. Sure. Okay, so let's move on. So last time we started talking about these benefit and cost curves and where the heck they come from. And so we said that these benefit curves tend to be concave. And the reason they tend to be concave is that interventions with the most added benefit tend to be pursued first. And so, and interventions with the least added benefit tend to be pursued last. And so you can see that if I make an intervention, if I remove 1 ton of pollution from the air, so that is going to, that first ton of pollution tends to be the one with the most benefit. To put it another way, if you're living in a world of smog, then if you can remove a ton of that smog, that's going to be huge benefits. So that's going to be great. But if you're living in a world where pollution levels are the point where you hardly even notice that there's a lot of pollution in the air, removing the next ton of pollution from the air is not going to make much of a difference. And so that's kind of where this curve comes from. And then the other curve is the cost side of things. And there's a kind of a flip side of that where intervention with the least added cost tend to be pursued first. Interventions with the greatest added costs are pursued last. So if you are making decisions about private compliance, you know, how do you reach compliance in your factory? So your factory is emitting too much pollution, so you want to bring it back in compliance. What you're going to do first are the cheap things. So you're going to turn off equipment that's polluting when you don't need it, for example. That's cheap to do. So, so that's, you know, happens first. And so the first ton of abatement that you get is actually the cheapest ton of abatement because you get it by just turning off stuff. But once you have made your factory as efficient as possible, there's no other efficiencies you can get out of it. The only thing you can really do is to start installing scrubbers and things like that. And those are much more costly. So for the last ton of abatement, it requires a huge cost. And so that's why the steepness of this thing changes. So these are sort of the typical way these things come together. So typically you get this football shape where the benefits of abatement, for example, have a concave shape and the costs have a convex shape. And then we are sort of looking for the level of abatement which maximizes the difference between the benefits and the costs. And so down here, the benefits are rising faster than costs. And so in this case, we generally are going to imagine that we're going to pursue more abatement because we get more out of it than we are putting into it. So that's a good thing. Over on the other side, the costs are rising faster than the benefits are rising. So at this point, if we add more abatement, we're just going to pay in for that abatement more than the benefit that we're getting out of it. So we'll probably do less abatement in this region. And the kind of sweet spot is in the middle, where the benefits and costs rise at the same rate. And so these lines here, which are tangent to these curves, are parallel to each other. And that's where we get the maximal net benefit. And so if we call these benefit functions BQ, where Q is the level of abatement, and cost functions CQ, where Q is the level of abatement, then this point here, I'm going to denote Q star. And the star is a common thing in optimization and economics to refer to the best or the optimal thing. And so the optimal level of abatement is this moderate level of abatement, where these two slopes are equal. So in other words, where the derivative of the benefit curve equals the derivative of the cost curve. Now, I'm rarely going to give you benefit or cost curves and actually have you do the derivatives. Instead, I'm going to do, and this is what most economists do, is just give you the derivatives instead of the raw benefit and cost curves. And that's what we've plotted here instead. Here you can see that this is effectively plotting the slope of those lines. The slope of the benefit curve is highest at low abatement and lowest at high abatement. The slope of the cost curve is lowest at low abatement and highest at high abatement. And where they intersect is equivalent to where those curves are parallel. And so at that point, the slopes are equal and the derivatives are equal here. And like I was saying, then from this perspective, the green area on the left here, this is that maximal distance between the benefit and the cost curves. And so like I said, if you were choosing a lower level of abatement, so if I were to choose my pen here, if I were to say we're going to abate this much, only a ton of pollution, then that is going to correspond to this area here. And so that right there is going to be, if I were to go back in the slides where I just had these curves, then that level of abatement is going to correspond to this difference between the benefit and cost curves. And we can see that that difference is smaller than this difference here. And that difference that we see at that lower level of abatement, that difference there corresponds to this area that I've kind of hatched out in red. And the maximal difference between the benefit and cost corresponds to the green area. So in kind of the magic of calculus, if you take the area between the benefit and the cost curves, you get the difference between the benefit function and the cost function. Sorry, if you take the area between the derivatives, so these marginal benefit cost curves, that area equals the difference between the raw benefit and raw cost curves. And that's what I'm sort of trying to say here in this note over here. Now, we don't use the term derivative very often. Instead, we use the term marginal. And so the marginal benefit is just the derivative of the benefit curve. And the marginal cost is just the derivative of the cost curve. So I will not usually give you benefit curves and ask you to do a little calculus. I know some of you are just working through calculus right now. Instead, I will give you the marginal benefit curve, which is my way of giving you the derivative ahead of time. And I will give you the marginal cost curve, which is my way of giving you the derivative of the cost curve ahead of time. And very often you will then set those two curves equal to each other and find the quantity that, if you solve that equation, brings the marginal benefits equal to the marginal costs. And that's equivalent to finding this point here, where the marginal benefit line intersects the marginal cost line. And then that level that you find is the efficient, and this is this term in economics, efficient. So it maximizes the difference between benefits and costs. Right. So before I revisit the condor example and answer the question that came up last time that I missed, are there questions about any of that math or the graphs? Okay, so our concrete example of a cost curve was this condor example. And so there was a great question from last time. So to sort of set this up, if we're reminded here, so we've got on the Q axis here, so you can think of it as this Q, this is condors saved per year. So you can think of the unit of this thing is in condors or condors per year. And then you notice that this cost curve, it jumps up in these kind of steps. And what is being referenced here is what way they've done is they've sorted different intervention strategies that each save a different number of condors per year. And they're sorted kind of by their cost. And so you can see that an intervention strategy that, habitat protection over here, then we can see that it saves 0.53 condors per year. So you can kind of see that this is where 0.53 lives. And so we jump over to 0.53 and then we jump up to the level of cost, and we say that it looks like it's $7 to $8 of condors per year. So on this axis, you can think of this as dollars per Q. So this is, that's the kind of this axis that we're getting very comfortable with working with. So this is the Q axis down here, and this is the dollars per Q axis here. So the dollars per condor axis is on the y-axis, the vertical axis, and the number of condors is on the x-axis. And so this point right here says that we save 0.5 condors saved per year at a cost of $7 to $8 of condors per year. And then our next intervention strategy here is we could say, well, we can actually save an additional 0.67 condors. So if you look the gap here between this point and this point over here might be 0.67. So we can save an additional 0.67 condors for 30 condors per year. And so or $30 per condor, $30 per condor year. And so if this box wasn't here, then we'd see that 30 would be behind this axis. So you basically can sort all of these intervention strategies, and the ones that provide you the cheapest amount of, the cheapest way to save condors are going to be the ones you pursue first. And so that gives this kind of shape here. And so up here, and if we really need to save additional condors, so let's say we've already saved 3 condors per year. If we really need to save more condors, then we can step up law enforcement. And stepping up law enforcement is not going to save that many more condors. So it's really not going to push us very much farther so I think they're actually highlighting this point here. If you look at that, it's not saving us that many more condors per year. But to go from this level to this level is a huge increase in cost. So it ends up terminating what's behind here. It ends up terminating way up here. So to pay people to go out and do law enforcement to save condors, they're pretty much going to spend most of their time not doing much because it's going to be really hard for them to find people doing things that are hurting condors. Occasionally they will, and they will save a few more condors per year, but they'll save super, super small amount of condors, even though we're paying them a lot of money. And so that's why law enforcement shows up, far on the right here. Now there was a question from the meeting pulse questions. Are the cheap options of saving condors cheap because it affects a small amount of condors in proportion to the total number of condors? What would the function look like if it were cheap to save a large portion of condors? And so the portion, so the fraction of condors is not kind of the unit we're here. It's actually an absolute raw number of condors. But the question is, what would it look like if it were cheap to save a large number of condors? Well, that's effectively habitat protection. For example, it is not saving. If you had a method that could save a lot of condors, 10 condors per year, and it was really cheap, then that would show up even farther down on this cost curve. So I just want to make the kind of the difference here is that condors are not the benefit. Condors are the commodity. Condors are the good. Condors are like the abatement quantity. So we're saying, how much good do we want? How many condors do we want to save? And this is only plotting the cost of that. If we have an option where we can get a lot of condors for cheap, then that option would get shoveled in right over here, and it would push all of the others down so that this curve would be flatter for longer, and then it would start rising. So that's kind of where it would be put in there. Now, you might think, well, aren't condors a benefit? Condors themselves aren't a benefit. Condors bestow benefit upon people who like condors. And so there is a benefit curve that is not plotted here that might look kind of like this, that would have that concave shape. And we would only be able to survey that benefit curve by going out and asking people things like, how much do you, and that, I'm sorry, that's the benefit curve, not the marginal benefit curve. So I meant to draw the marginal benefit curve. So let me maybe undo, I'll clear these annotations here. If I can, if it'll let me. Erase pen. So the, so this here is the marginal cost curve, just as a reminder. And the marginal benefit curve would go down like this. And that marginal benefit curve, we would get by asking people, how much would you be willing, and so this gets into kind of the next chapter. This is like, we could go out and ask somebody, you could say, hey, you know, Julie, how much would you be willing to pay to save a condor? How much would you be willing to pay to save 3 condors, and so on and so forth. Or we could ask them, how much are you willing to accept? We could say, you know, if we were going to kill all the condors, how much money would it take for you to be okay with that? How much would you be willing to accept if it was in exchange for us killing all the condors? And so by asking people those questions, we can then get a marginal benefit curve. And where that marginal benefit curve, which represents people's utility, intersects the marginal cost curve, like right here, this will tell us how much society is willing to save. So it's going to tell us that our society is willing to pay for all of these things, but it is not willing to pay for any of these things because the amount of condors saved doesn't bring enough benefit to justify those costs. So in order for us to figure out that point, we need to see both sides of the curve, the marginal benefit and the marginal cost curve. I'm only showing the marginal cost curve. And condors are not a benefit, they are a commodity, they are a good. The more condors we have, great, the more good. But we don't necessarily want to have all condors. And so we eventually choose a balancing point where it's like the optimal number of condors given the cost it takes to maintain that number of condors. So are there questions about that, about this cost-benefit analysis stuff, about the difference between marginal benefits and costs, the shapes of these curves, et cetera? And hopefully I answered the question that was given last time, and I apologize again for not seeing that sooner. Okay. All right. So the last part of this chapter, chapter 2, brought up discounting and time. And I want to now bring that into it. So right now we have only been talking about benefits and costs realized today. But in sustainability, we really also care about the benefits and costs realized in later generations, to us, perhaps, to our progeny, to their progeny, et cetera, et cetera. And so how do we, you know, I mean, at some point you could say that if an action I do today does not cause anyone any pain or any cost until 1,000 years from now, then that is going to totally change your calculus of saying that an action I do today causes, you know, 100 people today to not be able to eat. So if it's 100 people in 1,000 years, then you might say, well, you know what, I'm more willing to do that action than 100 people now. And so we need to sort of figure out how to model that in this kind of cost benefit framework that we've already been talking about. And so if we bring this back to the condors example, you know, we can think about this kind of, you know, a condor in hand is worth 2 in the bush. You know, so this is kind of, I'm trying to bring us to this kind of like more well-known saying, you know, a bird in hand is worth two in the bush. So this is an idea that if you already have a good thing, then you should just, that good thing that you already have is going to be better than two potential things that you might have later. And so don't give up what you already have just because you might have these two things later. Or even if you do have these two things later, for sure, then it might end up being more valuable to you to hold on to the one thing that you have. And so this is effectively comparing across time. It is making a statement about the equivalence across time is such that things later are worth less to you than things now. So, and this is what we do in economics when we do these cost-benefit analyses. We are going to try to convert the value of things that happen later into today's value, and then do a cost-benefit analysis in today's value. And so that's this sort of down here, what I've written out is kind of the economic version of a bird in hand is worth two in the bush. The so-called present value, the current value of two birds in the bush is equal to the present value of one bird in the hand. And that present value of one bird in hand is equal to one bird. So this is a statement that we discount things in the future by half. You know, that's sort of what we're saying here, and that's what we're building up to. So that's what we're going to be talking about today is discounting and trying to understand discounting and how we then make sense of discounting in terms of things like natural resource availability. That's where we'll end up ending. All right. So, so let's get a little more things about the framework, and then I'll open it up for questions to see if there's some confusion here. So I'm going to use these terms FV, future value, and PV, present value, a lot. Just standard terms we use. The PV is, again, the value that we experience today. The future value is the value that we will experience in the future, but we will not have access to after waiting a certain amount of time. And the future value is modeled as the present value times this funny little formula here, 1 plus r to the t, where t is the amount of time that you wait until you experience the future value. So if we have some equivalence between the future value you get later and the present value you would get equivalently if you just got it all now, then the claim is that that equivalence happens through this relationship here, where you take the present value and you multiply it by this, this here. And this should look familiar to you because this is just the same formula you use for thinking about your savings account. If you invest this much in your savings account today, PV and your savings account today, and you have a savings account rate that has an interest rate of R, then after, say, 1 year, so t equal to 1, then you will have a little bit more in your savings account. You will have your present value, the total amount of the present value, plus the interest added on top of it. If you let that stay in the savings account for another year, then again, you get more interest on top of that. And so that's where this formula kind of comes from. And so this is this idea where if you ask someone, you know, what's $1,000 worth? If someone will say to you, I could give you $1,000 now, or I could give you $1,025 next year. The question you ask yourself is, will the bank do better than this deal? Because if the bank will do better than this deal, I will take the $1,000 now and I will put it into the bank, and then I will come back in a year and I'll take it out of the bank, and the bank will give me more than the $1,025 that I'm being promised. But if this person is promising me more than the bank can give me via interest rate, then instead I will forego the benefits now and I will take the benefits later. So that's where this formula kind of comes from, is we're using the bank as a benchmark on how we value time. And so in order for us to then convert future value into present value, we're just going to divide both sides by this factor here. And so this is the formula we have here, where if I give you a future value and I tell you how far in the future it is, how many compounding periods in the future that it comes from, and I give you the interest rate, so how your discounting rate, then you can divide that future value down to find out the present value. So if someone says, I'll offer you $1,000 in the future, then what this tells you is how you divide that $1,000 down to find out how much that's worth to you now. And so $1,000 in the future might only be worth $900 to you now. And if you have another option where someone's willing to give you $925 now, then you can say, sorry, I'm not interested in your $1,000 in the future. I have another option who's willing to give me $925 now, and that's better. But if all of your other options give you less than $900 now, then you take the $1,000 in the future. So that's where these conversions come back and forth. So, all right, so before we keep going there, is this making a little bit of sense, or are there questions about this idea of discounting based on kind of the savings rate at a bank?
I got a quick question. It's just that, are we going to see this formula in action for some graphs, how the discounting works?
Yes, and so right, well, we're moving towards that, and then you'll end up doing math, just like the math you did on homework B5, but that math will then also have to involve these discounting rates, like I think in the next homework we'll do that.
Okay, got it.
So
thank you.
With that kind of math, are we given, if we're trying to calculate the present value, are we given the future value and would we be given FV, and T, or is that something we need to find in some way or derive in some way?
So in problems like that, what typically will happen is you will be in some way or another, like say a word problem or whatever, be given one of these values, typically the future value, and you'll be told how far in the future that future value is realized. And then you will be told a discount rate. And then you will then convert using, so you get future value check, you get periods in the future check, and you get discount rate check. And then once you've got all those three, then you can solve for present value. And
Okay,
so that allows, go ahead.
So it's plug and chug, but with really big applications.
Right, I mean, that's
Okay.
basically all of, yeah, time value of money, that's right. This is how people do in financing and accounting, whatever, it's this. And so, yeah. Any other questions? All right. Okay, so introducing other symbols here, it's just trying to make things look a little less ugly. So rather than carrying along this ratio, 1 over r, 1 plus r over t, I'm just going to use this value beta here. And this beta is just equal to this thing. It's just equal to this 1 over 1 plus r to the t. I just took the future value out of the numerator, I put it beside, and then I put everything else into a beta. And that allows me to use this beta instead of keeping around this thing. And that also allows me to more conveniently represent discount rates, say, in terms of word problems. So I already mentioned, like, a bird in hand today is worth 2 in the bush in the future. Well, rather than me figuring out exactly what the discount rate is, then I could say, well, this beta factor here is just equal to 0.5. So that's saying that, that's where it goes right here, that my future value, which is 2 in the bush, is equal to 1 in hand. And so this beta is equal to 0.5. So like I can see, 2 times 0.5 is equal to 1. So a bird in hand over 2 in the bush is equivalent to saying that this beta, a scalar factor here, which we'll end up having another name for, which you'll recognize here in a second, but that beta is equal to 0.5. Now, if I think about it, if I set my t equal to 1, then this just becomes 1 over 1 plus r. And if I think, well, then what discount rate corresponds to 0.5? Well, that would be equal to an r of equal to 1. And so that's like 100% discount rate, right? So 1 over 1 plus 1 is equal to 1/2, right? So this, 0.5 you can view as 1 over 1 plus 1. And if you want, just to make it clear, I'll put parentheses and I'll say, and this whole thing is 2 to the 1. And so having this beta, which I'll give a name in just the next slide, equal to 0.5 is equivalent to having the discount rate at 100%. And so, having this discount rate of 100% basically means that in order for me to reach equivalency, you've got to double what you're going to give me now. So having a discount rate of 100% means that rewards now have to be doubled in the future for me to take them seriously. If your rewards in the future are not double what you'll give me now, I have no interest. If they're triple, I have a lot of interest. So that's what I mean by discount rate. A discount rate is how much do I need to increase my present rewards in order for the future rewards to start being interesting. And so we are going to refer to this beta as the marginal rate of substitution with the future. Again, the MRS. So all this stuff that we've been evaluating in terms of marginal rate of substitution is going to apply. But now it doesn't apply to two goods that we have today. Like normally the marginal rate of substitution is like, I've got my fidget cube, which I don't have my fidget cube. I do have my fidget cube. So I've got a fidget cube and a green ball. And so I was wondering how many of these do I need to trade for one of these? Marginal rate of substitution right now. But now we're adding some more complexity to it where we're saying the fidget cube is in the future. And so now we're talking about the marginal rate of substitution with goods in the future. So I've got goods today and goods in the future. And what's the MRS between them? And so with that in mind, we can write the marginal rate of substitution with the future like this, the delta P over delta F. So how much change am I willing to make today, given a certain change that I get in the future? And this could go up or down. So it might be how much am I willing to forego today in order to get a gain in the future? Or the other way around, how much do I need to gain in the future, or how much am I willing to give up in the future to get gains today? So when this thing is equal to 0.5, which another way to view it is 1/2, then that means that if I get 1 today, I'm willing to lose 2 in the future. And so those are equivalent to me. So you could give me 2 in the future and I'll give up my 1 today, or you give me 1 today and I'll give up 2 in the future. So that's the marginal rate of substitution with the future. It corresponds, and in this case, the 0.5 corresponds to a discount rate of 100%. All right, now before I move on, where we're gonna get some more graphs involved, is that clear what I mean by the marginal rate of substitution with the future? If any of you have taken a finance class or an accounting class, sometimes this is called a P/F ratio. And so you say like, what's the P/F? And what's the P/F just means how do I scale my future gains in order to convert them into into current gains? Okay, all right, getting into graphs now. So if we go back, before we worried about time discounting, but we still had introduced marginal rate of substitution. Remember, the marginal rate of substitution was the slope of the indifference curves. And so as the indifference curves curved around, the marginal rate of substitution changed. So what if, though, I told you the marginal rate of substitution was constant everywhere? What does that tell us about our indifference curves? Does anybody remember or willing to offer up an answer, either microphone or chat? I see, so I'll wait for a couple other answers to come in or give me the opportunity. So what do the curves look like when the marginal rate of substitution is constant everywhere, where regardless of how much I own of every good, I'm always have the same marginal rate of substitution with the future? Seen a couple of answers in the chat. Anybody else? All right, so I've seen parallel lines and a bunch of negative slope lines, and those are both what I was looking for here, is that with your utility functions are all parallel, and if they all have negative slope, that represents that we have a constant marginal rate of substitution between these two goods. And so the slope of these lines, regardless of which line you're on and regardless of where you are on the line, are going to be constant. And so if we have a constant, rate of substitution with the future, then we would expect that some version of our utility function with the future is going to look like this. And that's kind of what, so this, by the way, this here is the utility function that corresponds to these lines. So if you were to say, all right, for any amount of good A and any amount of good B, you have this marginal rate of substitution here that I give you, say 0.5, for example. And then that moving, if I were to start on a bundle here that has a certain amount of A and B, if I were then to pick another bundle on this same indifference curve, and I were to calculate the utility U for both of those bundles, they would both be equal to the same thing. In this case, they might both be equal to a utility of 10. And then if I were to jump down here, we'd have other ones that if I were to evaluate this utility function for both, they both equal the same utility 9. And that's where we get these indifference curves. Now, when we think in the future, we now don't have two goods in the present. We kind of think of the future value as a good and the present value as a good. And so our present value I'm putting as the good on the vertical axis, and our future value is the good I'm putting on the horizontal axis. And this beta, this marginal rate of substitution with the future, it's going to be constant. And so our utility function in this kind of intertemporal space will have the same parallel lines. And so we refer to this thing down here, which takes the place of the utility function, as an intertemporal social welfare function. So a social welfare function, or an SWF, not single white female, but SWF, social welfare function. This is a function which combines utility across different, we usually think of as different agents. So it could be, me versus you. So how do we combine utility, in a society, how do we combine those together? So we have a social welfare function which combines my utility with yours. We also think about me in the future as another person. And so I'm combining the utility I experience now with the utility I experience later. And I'm viewing me later as kind of a different person. And I think that's reasonable. I bet there's a bunch of times you've thought of where you could have made a decision differently that would have caused you less work later, but you kind of said, I don't really care about that person later. I just want to deal, I want to make things easier for me now. And that person later, they can worry about that later. So I'm not going to do this. I'm going to put this dish in the sink. I'm going to let later me deal with this dish. And I keep doing that. And then later me has to deal with 100 dishes later because present value me decided that they were willing to do it. So really the later value of you is almost like a different person. And that's why we view this as more than just a utility function, but actually a social welfare function. It combines utilities where we can think of the present value as one utility and the future value as another utility. And this beta value is our how much we're willing to substitute. So eventually you tell present value me, if you keep doing this, you're going to have to wash 1,000 dishes in the future. And at that point, present value me says, all right, I'm going to start doing the dishes. So I made a switch where suddenly the future value, or the future, in this case, the future cost was so great that I was willing to take on a cost in the present. So there is a substitution where eventually the cost gets so large in the future, you're willing to take action in the present. And this beta represents that tipping point where you go beyond that, and then suddenly you're focusing on future returns or costs, and below that, then you're focusing on current returns or costs. And so this is what those social welfare functions would look like if we plot future value as a good and present value as a good. Okay, so before we move on to see what we do with this, are there questions about this framework? Again, we're just revisiting all the utility stuff we've done, but now we're defining a good as a good in the future, as opposed to a good that we currently have. And it looks like there was a question, but then a never mind, but other people might have had the question. The question is, social welfare is positive. Does that mean you do the dishes now or later? I guess, so social welfare, I guess I should say that this beta is, so this this beta, so yeah, is if social welfare is negative. So social welfare will always be positive, but the rate of substitution, it's kind of like the marginal rate of substitution. By convention, we make it positive to represent these negatively sloped lines. Now, if we have a bad and a good, it is possible for this beta to become negative in itself. So if the question is, how much bad am I willing to tolerate later for a good now, then that model might involve a negative beta, the same way we can get negative marginal rate of substitutions when we kind of combine goods and bads together. But generally, when we combine two goods, future good and current good, then this beta is going to be positive, just like in the utility sense. All right, so now we've got this utility framework with indifference curves. Now remember, in consumer choice, once we had the utility curves, our next step was to define a budget constraint line in order to give us an idea of what choice we would make. What is the optimal choice for someone to make when facing this? But whereas before, it was easy to come up with our budget constraint line because it was like, well, I know this fidget cube costs this much, and I know this squishy ball costs this much. So I can figure out how many squishy balls I can buy and how many fidget cubes I can buy based on my current income. But this becomes harder to do when you think about over time, because you think about this, you're like, well, I get a paycheck this week, but I also get a paycheck next week. And so the budget I had for this week, how do I couple that with the budget I had for next week? Like, it becomes hard to come up with a budget constraint line. How do I convert these goods that I can't even think of buying until the future? You know, like, what is my equivalent of a budget when I spread things out over time? And that's something that we need to handle next. And so, and I hope it'll be kind of obvious that whatever we come up with that will be our stand-in for the budget constraint line is probably not going to be a straight line. Because as we learned towards the end of Unit B, then we learned that this budget constraint line, if it's straight and if the marginal rate of substitution is straight, then what we're going to do is just specialize on the good that's on this axis, because the budget constraint line is steeper than the indifference curves. And that would mean, in this context, only focusing on present value. And we know that that's not actually the case. It's very rare that we're only going to focus on present value. And so clearly there needs to be a way for this to model us thinking about both the future value and the present value simultaneously. And so our budget constraint line is going to be more complicated. So basically, where the utility lines are, the indifference curves are lines, our version of the budget constraint line over time is going to be the thing that's curvy. And so that's what we're getting into. And so the way that we get there is through scarcity. And so rather than thinking about, if I'm only focused on the current time, the thing that is the major limiting factor in my decisions is my budget. It is how much do I have available of dollars to spend. If we think about decisions made over long periods of time, then the thing that we need to focus on, which could also be dollars if we do it kind of the right way, but we can also think more generally about natural resources, is scarcity. So the choices I make now, the dollars I spend now, so imagine you were living on a fixed budget. Your budget did not get replenished. If you had $100 to spend over your entire lifetime, then your choices now would necessarily couple to choices later. And so that is what we're trying to kind of get, is a kind of lifetime budget. And natural resources provide us that lifetime budget because there's a fixed amount of them if they're non-renewable. And so that's the kind of what we're going to think about. Imagine a non-renewable resource where your choices now are going to use some of that up. That's going to prevent you from using that later. And if you use all of it up today, there will be none available later. And so if you use all of it up now, the only benefit you're going to be able to get is the benefit you get now. And you're not ever going to be able to get a benefit from it later. And that is going to sort of impose something that acts just like a budget constraint. So that's where we're going with this. And I've listed, all these different, things, water, so these are different areas of the world that have different amounts of water scarcity. And so you can imagine that the decisions made in an area with severe water scarcity are going to be different than the decisions made in an area with lots of water. And that's because water acts like a budget. If you make a high income, you make very different purchasing decisions than if you make a low income. So again, scarcity acts like a budget. Okay, so let's see how that's worked out here, and then we can see if you have questions about that. So what is going to play the role of our budget is the total amount of a non-renewable resource. And so we're just going to call that T. And so that is the total amount of water that I have, total amount of oil that I have. That is the maximum amount of oil that I can get out of the ground, total. Now, for simplicity, we're only going to focus for the moment on two periods, my present period and a future period, a single future period in the future. And so the idea is I could extract oil from the ground now, or I could extract oil from the ground later, or a mix of both. Now, if I extract from this and use this oil up, I'm going to consume, so Q is going to be how much I extract in the current time period, and that's going to be necessarily less than the amount that's available. And then I just assume that all the rest is available I use in the next period. So that's all the rest of the variable I use in that next period right there. So I'm going to get a benefit in this period from using up Q, and I'm going to get a delayed benefit for the next period that I'll have to discount for T minus Q. So for every choice of consumption now, there's a benefit now and a benefit later. And my goal is to combine these two benefits together to understand kind of the present value of both benefits together, so I can then understand what the optimal level of consumption is between my two periods, this period and next period. So this will define what economists call the production possibility frontier, which I'll show you in a second, or the PPF, or the production possibility curve. And this basically is going to be all combinations of utility, all combinations of outcomes that I can get from choosing different amounts of usage now and later. So to show what that looks like, if I go back to my present value, future value curve here, then basically you can imagine that, so this production possibility frontier is the kind of, it's what's possible if I pull out some level Q from now. So I pull out some amount of oil from now, and then all the rest of it later, then I will get a certain, and if I use all of that Q as efficiently as possible. So let's say I sell it to the marketplace and I sell it at the best possible price, and I sell the stuff next year when I draw it out there at the best possible price. So as long as I capitalize on it in the most efficient way possible, then what this curve up here gives you, this kind of the dashed lines in this curve, are all possible ways that I can mix my present value and my future value. And so if for example, if I extract all of it now, then I can only get present value. I cannot get any future value, and that's why my future value is equal to 0 and my present value is equal to here. Now there might be a mixture where I extract less than all of it now, and due to the economic efficiency arguments, and we'll go into this in more detail, then I actually maximize my present value, and while still leaving over some for future value, and so on. And so the question is, where do I want to sit on this curve? Now, of course, there are less efficient ways that I can extract this resource. I can extract this resource and burn it, and I don't really get any benefit out of that. And so all of the outcomes down here are the attainable outcomes that I get for kind of the least efficient ways of using all of that resource. Or another way to view it is if I don't extract all T units of the resource, I leave some in the ground, then I don't get all of the value I can get across these two periods. So this production set is equivalent to the budget set when we had our budget constraint line. So the budget constraint line was if I spend all of my budget these are all of the things that I can buy, all the mixtures of things I can buy, and anything under the budget constraint line, or if I don't spend all of my budget, I can buy these other, I can buy these mixtures. And so everything underneath here is if I don't spend everything, or if I spend things in kind of a way that doesn't bring me maximal utility, then I'm in the light green area, but I'd like to be in the edge, which is if I use all of the resource, but I distribute it across present and future, I'm going to be somewhere along this line. Okay. All right, so I already mentioned this example, and maybe I'll pause here for questions. Are there questions about this curve?
So are the attainable outcomes always in a teardrop kind of shape, or could they have like crazy wiggly lines?
Excellent question. And yeah, that's a great question. This teardrop shape is going to be pretty common. And in the next lecture, which is, I mentioned this, right, it'll be asynchronous. So in the asynchronous lecture, I will go into this a little bit more detail to show you where that teardrop shape comes from. But I hope you'll start seeing it already. And that this teardrop shape comes from the hump shape of economic efficiency, how there is an intermediate level. So if we think about the current period, we know from the chapter that the benefit function is concave, the cost function is convex, and the area in between the two has kind of a maximal point in the middle. And that gives a hump shape of our net benefits in the present period. And that hump shape in the present period is going to also mean that there is a, so if I view this as my Q, so my present period, then I know that there is some intermediate level in the present period, Q star, where I maximize my present benefits. And there is a similar hump shape in the future period. It is these hump shapes which set up these teardrop shapes, because what these hump shapes tell me is that if I did put everything into the present period, Q equal T, then economic efficiency tells me that if the cost it takes to extract every last drop of oil is going to be so costly that it is not going to be worth the benefit for me. So I am going to necessarily want to leave some oil in the ground because it's going to be costly to get that oil out, at least this year. So for some reason, I'm assuming that next year it's easier to get it out, and we'll have to table that discussion for later. But for now, we're saying if I did wanted to get all of it out, then I'm actually going to get a decrease in my net benefit. So this intermediate level, which gives this hump shape, also gives this teardrop shape, because it's saying that if I put everything in the present, I will get a present value out, but it's actually going to be better for me to leave some oil in the ground, and that corresponds to this thing right here. So that corresponds to this. And although I could just leave everything in the ground, in which case it would be all future value, which is over here. And so this teardrop is, going from this point down here to 0, and then all the way up to this point in present value, and then back down to this intermediate point here, is actually following this. And if I kind of put this curve on the present value axis, and I do the other, the future value with a similar shaped curve, then I end up matching the two of them together, and I get a teardrop. And I will do that more graphically in the next lecture so that it's a little less hand-wavy. But I hope you can kind of smell that coming.
Okay, thank you.
Any other questions? So which is the maximum efficiency over time? Excellent question. That's where we're going. So right now we know what the maximum efficiency for the present value is, but we don't know what it over time. So this is the maximum efficiency for the present value. We get that by doing, we don't worry about the future value. We're only focused on the present value. And so if we were to do benefits or costs just based on the present value, it would tell us not to do all of the oil, just to do some of the oil, leave some of the oil in the ground. And this is the old math that we were learning would put us at this point. And so it's kind of like the old math we were learning, ignored the future value and just maximize the present value. If instead we maximize the future value, so we did not convert to present value numbers, we just maximized the future value numbers, then we basically pick this point, which will basically say, pick the amount of oil that you're going to get next year from that period, and just assume you can get as much oil as you want. And so if you have access to all of the oil, do the same cost benefit analysis that we did for the present value, but just pretend and do it for the future value, and don't do any discounting. Just do it all for the future value and maximize the future value. And that's where you would be at this point here. And so, and then, you know, or if you instead just said, in the future, I'm just going to do everything. I'm just going to just pull it all out of the ground in the future and don't do any today, then you'd be at this point, which does not maximize the future value. The same way, pulling it all out now does not maximize present value. There's a value to having some left in the ground now. And if you were just focusing on your decision-making later, there may be a value of having some in the ground later. So so that's how we move around the curve. And what you can imagine then, that there is, just like the budget constraint line has an opportunity cost, which represents how much you have to give up to move from one bundle to another to stay on budget. Then if you want to move from this point on the PPF to this point on the PPF, then you can imagine we could put a line that is tangent to this point here that would kind of represent that opportunity cost calculation. In other words, for this production frontier, how much do I have to give up in the future to increase my amount in the present? So we can see here that in order for me to move up in the present, I necessarily must move back in the future by a certain amount, just like moving along that budget constraint line. And the slope at any point along the production, the PPF, is known as the marginal rate of transportation, of transformation, or MRT. So this is a lot like the price ratio. The slope of the budget constraint line was the price ratio. The slope of the PPF at any point along there is the MRT. So like I said before, it was the utility functions that had a changing marginal rate of substitution. Now the marginal rate of substitution is fixed, and the marginal rate of transformation is changing. And so it shouldn't surprise you that what we're going to end up finding is that there's going to be an equimarginal principle that will tell you exactly what the optimal consumption level is between those two. So just to make that hopefully a little clearer, I'm going to throw up the social welfare curves again. And what we see with these social welfare curves for this particular discount rate, so this particular P over F value or beta value, then we get these social welfare curves. And we can find that they run tangent to the PPF at a particular point here. And what we're going to find is that that is the optimal balance of use from the present value and the future value combined together. So at this point, that is exactly the point where the slope of the PPF, this outer dashed line, is equal to the slope of the social welfare function. It's where the MRT, which is the green slope, is equal to the MRS, which is the slope of the utility functions, the social welfare functions. And so that graphically is how we find the maximum efficiency over time, as we ask, where do these two things intersect? And so if we, for example, assume that we have a P over F value, or a marginal rate of substitution for the future, equal to 0, what that means is that I don't care how much future value you give me, I will not sacrifice any of my present value for any of your future value. This means I do not care about the future one bit. All I care about is the present. And that is going to give you horizontal social welfare curves, horizontal utility functions, horizontal indifference curves. And not surprisingly, that then gives us, they are tangent with the PPF at the point which maximizes the present value. So this is the largest present value I can get out of the PPF, and that happens to be where those are horizontal. So now I can flip that around, and I can say, what if I only care about future value. I do not care about the present value. Well, that would be a marginal rate of substitution that would be infinite. So that would mean that it doesn't matter how much present value you give me, I am not willing to sacrifice any of my future value. All I care about is my future value. And so this would be one of these weird cases where the discount rate would be negative 100%. So that's the way we get this. And for this weird case, which you'll never consider, it'll never be the case that you only care about future and you don't care at all about the present. But if you were in that weird case, you get vertical social welfare lines. And those vertical social welfare lines are tangent to the PPF at exactly the point which maximizes the future value. So this point here, that is the maximal future value. And so if we then consider intermediate values, then we end up finding blends of maximization of the future and the present value. So in our in this, if the marginal rate of substitution is 1, then that means that I have for every unit in the future you give me, I'm willing to give up 1 unit in the present. So it's kind of like I care about the future equally as much as I care about the present. So in that case, I get these 45-degree angle social welfare functions, in which case they end up being this balance of the PPF, where if I were able to bring this back, then I find that my utility for both the future value and the present value is equal. So I have not biased my calculation. I basically get an equal value from both the present and the future. And that's, corresponds to my equal valuing of present rewards and future rewards. Now, more realistically, I am probably going to care more about the present. And so this is in the range of values where my marginal rate of substitution with the future is between 0 and 1, and is usually strictly between 0 and 1, like 0.5, a bird in hand is worth 2 in the bush. And in that case, we gradually tilt those social welfare curves so that they move upwards, so that I'm not quite at the present value maximizing, but I'm very, very far away from the future value maximizing. And I'm probably pretty far away from the present is equal to future value case. And so I'm somewhere in between here. So as you increase your discount rate, as you increase your discount rate, you're going to decrease this beta, which is going to make these slopes shallower. And as they become more and more shallower, then you're going to move more and more towards present value maximization. As you decrease your discount rate, then you're going to make your marginal rate of substitution steeper. And as it becomes more and more steep, you're going to move closer and closer in this direction. And so we focus on this swinging from back and forth as we've got present value maximization here, and we've got kind of like present is equal to future here, and we're usually somewhere in between. And so that's graphically how we solve these things. Realistically, we convert, if I were to give you a marginal, and I'll do this on, I think, a future homework, if I were to give you a marginal benefit or marginal cost curve in the future, one of the first thing you need to do is multiply it by the discount factor, or multiply it by beta. And after you multiply it by beta, that turns the marginal benefits in the future into marginal benefits in the present. If I give you marginal costs in the future, you multiply them by beta, and that turns them into marginal costs in the present. And then you can do the same marginal benefits equal marginal costs in present value. So then you can do the, equate MB equal to MC, as we'll see more of in a future homework. But graphically, this is what we're doing. And if you get used to these graphs, it becomes much easier to reason about what happens as people increase discount rates and decrease discount rates. All right. So we're almost at the end here for today. Are there questions? And again, we'll use more concrete numerical examples as we move forward, but I want you to sort of be motivated by this idea that all we're doing with all of this present value, future value stuff is just the same stuff we've been doing with our utility curves, but we are now doing them where we're considering goods that are kind of distributed into the future. And we just have this funny thing where now our budget constraint is this funny production frontier, where now the budget constraint is curved while the utility lines are straight. But otherwise, it's basically the same reasoning. There's the same equimarginal principle. So any questions?
So if we were to do this, marginal rate of substitution would be anywhere between 0 and 1 in that specific area, or does that be where in the exact middle?
If you gave me a your marginal rate of substitution with the future, and all practical problems will be between 0 and 1, and for this graphical depiction, then at 0 it'll be at this point up here, and at 1 it'll be at this point here. And if it's anything in between, it'll be anything in between. So the rest of this PPF will be unexploited. So it'll be kind of irrational to be in the rest of this PPF. You'll just be focusing on solutions here.
Okay. All right. Thank you.
Okay. And I'll give an attendance question in a second here. Any other questions? All right. Okay, so the attendance question. So somebody already provided the attendance question in the chat. Thank you for that. I guess I'll just, as a habit, I'll also put it in there. The attendance question for today is what is the PPF? So just what does PPF stand for? So I guess I could say that again. What does PPF stand for? So again, these aren't graded for correctness. They're just graded for completion or coherency. So, but just trying to get you used to the lingo. If you have any other questions, I'm happy to take them. It's 1:13 right now. If otherwise, that's all I have for you for today. Remember that Thursday is going to be totally asynchronous. I will send out a Canvas announcement, and then I'll pre-record the lecture and post that so that you have that available. But there still will be attendance questions on Thursday, but it'll just be, you'll tune in asynchronously instead of synchronously. And it's just, unfortunately, this panel happened to land, it's prearranged and just landed on Thursday, so.
Professor, I have a question really quick.
Yeah.
If you don't mind. So I'm having a hard time getting the vocabulary down. I just see a lot of words and I'm like, okay, and especially working through problems, and I'm like, okay, what is this? Do you have any recommendations on what I can do to help internalize it and just kind of get the vocab down pat?
That's a good question. I mean, some of it is practice. I would try to look for these fundamentals. Like if you'll notice things like marginal show up a lot. And so, marginal always means, the next unit. So if you see a term that has marginal in it, before trying to figure out what that is, you should think that it must be a relationship between, if I currently have my current state of ownership, I am thinking about my relationship with the next unit that I can pick up. So marginal rate of substitution is given how much you currently are allocating to future and present value, how much are you willing to trade to make a small change, marginal. Substitution versus transformation. So, substitution, I'm really willing to trade you this much now versus that much later. Transformation is a little bit different because it refers to this frontier of, it's like a budget where if I have a budget constraint, the only way I can transform a thing I own into something else is by selling it and then buying the other thing, and then I've kind of transformed it. So that's kind of where the marginal rate of transformation is more on this kind of like, what can I do with my budget? Like, how can I transform the things I have? Whereas the marginal rate of substitution is more like, if someone were to come up to you and say, I don't care how much money you have, I'm willing to give you 100 of these things. How much would you be willing to give me of those things? So the transformation is like subject to your current constraints, where the substitution are kind of like regardless of what your constraints are, how much you're willing to give up. But they both have marginal, which means it's the next unit. It's not like all of it. So, and then rates. Rates generally mean that there's going to be you're dividing one thing by another. So, how many of this per that? That's a rate. Those are, I mean, it's just kind of you get used to it because you start noticing kind of a common construction. It's kind of like learning a language. It's really hard to learn a language when you only know a couple of words. But once you learn a bunch of words, you start noticing patterns that, oh, subjects always come before verbs, et cetera, et cetera. And that, that will become more clear as we move, but it'll just take practice, I think.
Perfect, thank you.
Any other questions? All right, don't forget the homework's due on Sunday. I should still have office hours on Thursday, and I'll send out an announcement about the asynchronous lecture on Thursday. Okay, well with that, I will go ahead and end the meeting. And if, and I guess the next time I'll synchronously see you is next week. So we'll have a good synchronous weekend, even though we will asynchronously see each other on Thursday. Yeah, and have a good week.